Good day, everyone. Welcome to today's webinar on PFAS in the environment, sources, behavior, and remediation at infrastructure and manufacturing and waste sites. This is the third and final part of our three-part series on PFAS. And today's webinar is going to be presented by Ryan Schipper of Golder Associates. Ryan's a senior engineer with Golder. He's based in Fort Wayne, Indiana, where he specializes in wastewater and leachate treatment. He's a registered professional engineer with over 11 years of experience in active and passive treatment projects, both in North America and overseas. His projects have included alternatives assessments, treatability studies, preliminary cost estimates, preliminary detailed design, construction oversight, and startup support. Before we get going, just a word about this webinar. We're going to go for about an hour today. There should be time at the end for some questions. So please feel free to type them in as we go, and I'll be monitoring them, and we will bring them up at the end. So don't forget about that. And in the meantime, we'll turn it over to you, Ryan.
Thanks, Guy. As Guy mentioned, today I'll be discussing PFAS at waste management facilities and also remediation strategies for PFAS. So Stefano may be joining on, but I think he was having some connection issues. But I'll run through this through the presentation here. So I'm going to start out with a very brief PFAS overview, just for those of you who may not have joined the previous calls. This is going to be pretty quick and just a real high-level overview. PFAS refers to per and polyfluoroalkyl substances, which is a large class of compounds, many groups. We're mainly interested here in the orange groups shown, which represent the compounds with completely fluorinated carbon molecules. The carbon-fluorine bond is a very strong bond and difficult to break, which is part of what makes these constituents somewhat of a challenge to treat at times. So within these perfluorinated compounds, we have the perfluoroalkyl carboxyl acids, which include the PFOA, and the perfluoroalkyl sulfonic acids, which include the PFOS. So you can see those in the bottom left of your screen there. There's also many of the other families or groups that are not in orange. There are precursors. So these are larger compounds that can break down into terminal completely fluorinated compounds, which would be the orange families or groups. So PFAS uses, it's been in use since the 1950s. You know, it's because of those carbon-fluorine bonds, it has a number of different very versatile properties. It's used in a very wide range of industrial applications. We all know the AFFF. There's also fluoropolymer production applications. These include Teflon, Gore-Tex, your Stain Master, and Scotchgard. We've got metal plating, electronic, semiconductor applications as well, etc. It's also present in many different consumer products. So we treatment coatings for cookware, the Teflon, different paper and anti-stick on paper, leather, textiles, for waterproofing, glass, stone for water, oil, and stain repellents, and also, you know, I won't go through all of them, but a number of inks and paints and other different liquids that have PFAS in it. So that's kind of, oh, sorry, Guy.
No, I know we saw this slide the last webinar, but one thing I didn't appreciate, you know, things like Scotchgard, which I grew up with and coated my university couches with to try and keep the stains away. You can't get those anymore, eh? And the idea, the Teflon frying pans, which so many people have stuck in their cupboards, I gotta assume you can't buy Teflon frying pans anymore. Is that right or no? Do you have any idea?
Well, so there are certain PFAS that are now that you can't manufacture within the U.S., but they can still be manufactured overseas and brought in. So there is, you know, a phase out, and there is less of it being manufactured here in the U.S. But you know, there still is PFAS in a lot of products that are available today. So great.
Wow, thanks.
So this is the high-level PFAS overview. Just kind of throwing out all of those different products, because as we talk, obviously a lot of these products can end up in a landfill. So I'm just keeping that in mind. So with that, I'll give a real high-level regulatory overview to help understand some of the drivers at different waste management facilities. Drinking water, groundwater, and surface water standards. Canada has drinking water, groundwater, and surface water standards for PFOS. These are the federal guidelines. Canada also has some provisional standards. BC has some standards for PFOA and PFOS. The Australian federal standards are shown there. There are standards for PFOA, PFOS, and PFHXS for drinking water. You can see I won't jump into them, but overall these are in parts per trillion and relatively high to maybe some of the other standards in some other countries. There are standards in Denmark, Germany, Italy, Netherlands, Norway, Sweden, and the UK, as well as the US. And I'll have a little slide on the US. There's a number of different PFAS contaminants that have standards, and the levels at which those standards are at are quite variable. Norway and Sweden have some of the lowest levels or standards for PFOS, and in some cases less than parts per trillion range, so very low standards there. The U.S. Drinking groundwater and surface water standards. So we have the U.S. EPA with the health advisory that combines 70 parts per trillion for PFOA and PFOS. This is there isn't a number of actual drinking water and other standards yet. So this health advisory is a lifetime exposure limit. So there's room for the US EPA, and it's taken them some time to bring out some of the standards, but the states are starting to fill that void with a number of different regulatory approaches, and sometimes that can get confusing. Here is shown a number of the different states that have their own standard or guidance for drinking water, groundwater, or surface water. There's actually additional PFAS compounds that are regulated, but these are maybe some of the more common ones, or that more of the states have standards for. So just kind of an overview. I'll draw maybe the attention to some of the low limits in California. You can see, all of these values are actually in parts per billion. Yeah, so California there, the 13 and 14 parts per trillion. Michigan also has some very low standards, New Jersey and Vermont. With that, so these are the states here that have different standards. There's also a number of states that have effectively adopted the US EPA health advisory, and those include Alaska, Arizona, Colorado, etc. As I mentioned, there's a number of other standards or other PFAS that have standards, and that's kind of shown there. This is from the ITRC, which was updated November 15th, 2018. There may be, there's much of the regulations are quickly changing. There may be, some updates to that, but this is pretty current. So then we'll talk a little bit. So the waste concentrations and what Australia is doing, and they're developing some PFAS concentration limits to regulate PFAS. Essentially different thresholds to determine how you're going to dispose of that, whether if it meets the thresholds to dispose of within an unlined landfill, or if it needs a clay single composite lined or double lined cell, essentially. The waste concentrations must be less than both the total relevant and leachable concentrations from the Australian standard leaching procedure. And that's conducted at both a pH of 5 and with unbuffered reagent water. So approximating, which is really there to approximate the worst case for leaching.
Hey Ryan, is it fair to say that that Australian leach procedure is it's analogous to the T-clip?
It's a similar procedure. There are some differences, as I understand, but yes, I mean, on the whole, I believe that you can use the SPLP or the T-clip, which would be used in the U.S., so that the pH is a little bit different. But yeah, very similar procedures. So another way that some jurisdictions are managing PFAS is by regulating leachate and other PFAS-containing effluents. Michigan is requiring wastewater treatment plants to investigate PFAS concentrations in their wastewater streams that they're receiving. So a number of different landfills and other sources that are discharging to Michigan POTWs have been being forced to sample for PFAS. There, is likely kind of reading into it. They may be required to pre-treat if they're over some of the concentration limits going to the POTW or the wastewater treatment plant. If that wastewater treatment plant is discharging above the standards set for Michigan. Vermont has another approach for PFOA and PFOS. They have guideline levels for concentrations that can be accepted at landfill leachate. So there's a threshold where if you're over that if you're under, there is no restrictions, and then there's a threshold where there is potentially restrictions for a certain range, and then if you're over a certain concentration, then you require pre-treatment for PFOA and PFOS. So some of this, just to put this into a little bit of perspective, we talked a lot about some of the limits. Many of them are in the parts per trillion range. And I think it's kind of important to understand, what we're talking about and maybe a little bit of the difference between a parts per million and a parts per trillion mindset. So 1 gram of PFOA can impact 3.7 million gallons of water and essentially put that above the 70 parts per trillion if we're looking at the US EPA standard for combined PFOA and PFOS. That obviously, we're looking at very minute quantities here. Air deposition rates in the single digits can be detected in groundwater. It's important to understand with these low levels that residential and small scale commercial activities can be a significant source of PFAS impacts. And we need to a lot of times proceed with caution and diligence and understanding the sources and where they're coming from. So I think to further put this into a little bit of perspective, kind of looking at an easy way to conceptualize the different concentrations. So if you're looking at parts per million, this is essentially 1 1/4, 2 liter bottles of whatever constituent in an Olympic sized swimming pool. When you drop down to the parts per billion, then we're talking about half a teaspoon within an Olympic sized swimming pool. And now then when we get to the parts per trillion, which many of these PFAS are regulated to, this is essentially equivalent to a part per trillion is essentially equivalent to 1 drop of water in 20 Olympic sized swimming pools. So I think that provides a little bit of a context for what we're looking at here. And there's another quick example that may relate to others there with, I think that those are pallets of $1 million each and $100 bills, and kind of showing what $1 million looks like and in comparison to trillion.
I think that's a good description of the U.S. annual debt.
Yeah, that looks about right. So it's sometimes hard to wrap your mind around some of these very large or very small numbers, but anyway, for me, that kind of helps put it into perspective. So with that, we'll go through a little bit of some considerations of PFAS at waste management facilities. We've kind of talked a little bit about some of the regulatory background and drivers. Here we have what I call the PFAS cycle. So at the top of the screen, that represents manufacturing, which has resulted in PFAS products and byproducts being produced over the last 60 years. Different PFAS containing waste have then been discharged to a lot of different wastewater treatment plants from those manufacturing byproducts or in some cases products. And though the wastewater treatment plants during their treatment typically don't remove large quantities of PFAS, they pass through. However, there is a significant amount of PFAS that ends up partitioning onto the biosolids or sludge. It's maybe also interesting to note too, and I guess we'll get into some of the precursors I think a little bit later in the presentation, but many times these wastewater treatment plants, even with these, the biosolids having a lot of PFAS in them, they can have higher terminal PFAS concentrations, so those completely fluorinated carbons molecules in the effluent when compared to the influent, and that's really because of the breakdown of a lot of different precursors into those terminal PFAS compounds. So the biosolids and the sludge that's produced from the wastewater treatment plant, though that typically can either be disposed of directly in the landfill, in some cases land applied. There's obvious concerns, I guess, with both of those, and then we also have other inputs into the landfill, which would be PFAS containing waste or byproducts. So at the end of these products, at the end of their useful lifetime, oftentimes end up in the landfill. So those are the sources into the landfill, and once we get the PFAS into the landfill, because it is PFAS a lot of times is relatively weak partitioning, you will end up with high concentrations of PFAS within the leachate. And where does that go? Well, in many cases in the US, at least, and a lot of other areas in the world, that can then be discharged to the wastewater treatment plant. Well, I think you guys can all see the continual loop, and we complete the cycle, at least with the biosolids and going to the leachate. There's also another possibility for PFAS, and this is mainly precursors being discharged out of the landfill gas. So being released to the atmosphere and then falling out it is another potential release from landfills. So kind of just to highlight that a little bit, the areas of concern for waste facilities, in terms of PFAS coming into the landfill, we have PFAS containing waste. We have PFAS in biosolids and sludges that can be directly disposed of in the landfill. There could also be on-property management, blending, composting, stockpiling with PFAS sources. And sometimes these biosolids and sludges have been used for final cover material. So if the PFAS compounds aren't solidified or stabilized, and we can get leaching of that going out into the landfill and then having issues with the leachate. So the PFAS out, obviously the big one is the leachate. The Solid Waste Association of North America, Swan Eye survey, almost half of the leachate treatment, or sorry, almost half of the landfills in the US discharged directly untreated to a wastewater treatment plant. And there is a percentage as well that discharge treated leachate. However, in many cases, the treatment processes for the leachate treatment plant, they're not addressing the PFAS. PFAS can also be in the landfill gas, again, typically with the precursors, the potential there. And then you also have the potential for PFAS releases to the groundwater or surface water if you have issues with a liner or other releases. So to touch a little bit more on some of the biosolids and sludges, here's a study that shows some of the biosolids, and these are in micrograms per kilogram or parts per billion. So if you convert that into parts per trillion, you in some cases have PFOS in the 400,000 parts per trillion range in some of these biosolids and amended soils. So there's obviously concern there with those concentrations when we're looking at very low levels of PFAS. Paper fiber sludge.
Hey, Ryan, just a question here. When you say biosolids, you're talking mainly about the biosolids from wastewater treatment plants?
That is correct, yes. So those biosolids can be used to amend soils. They in some cases, and they're also discharged or disposed of in landfills.
This is the same stuff that I think I said in a previous webinar. You can go down to your local store and sometimes buy bags of nutrient-rich soil that's come from the treatment plant. I don't know if they're still doing that, but you sure used to be able to do that.
Yeah, there can be concerns around that for sure. The paper fiber sludge is another source that can contain very high levels of PFAS, sometimes in the tens of thousands of parts per million. Again, that's a few percentage points of the total weight can be PFAS, and some of these have been sampled, I guess, in some of these paper fiber sludges. So obviously, using something like that for a daily cover would be an obvious concern if it's not stabilized. So the leachability here is.
Just a question on the paper fiber sludge. What industry are we talking about? Paper manufacturers or paper recyclers, or what is it? Where is this stuff coming from?
It can be both. There's a lot of different waterproofing and anti-stick properties on certain papers, so that's where a lot of the PFAS is coming from. So PFAS in landfill leachate, there's a number of different studies that were performed. U.S. landfill, number of different U.S. landfills in 2017. They found that 18 landfills and took 95 different leachate samples. There was over 70 different PFAS measured, and there's only, even though there's thousands of PFAS, we're only commercially measuring a fraction of those. But 19 different PFAS were detected in greater than 50% of the samples. The PFOS, I won't go into all the, you can see them there, but I will note that in some cases, landfill leachate can have PFAS concentrations all the way up into 100,000 parts per trillion for some of those landfills that have maybe taken direct sludge from PFAS manufacturing, or were near some of those manufacturing facilities, and they could have taken sludge from a municipal wastewater treatment plant that treated some of those byproducts. So it can be even significantly higher than some of the concentrations shown here. There's a Canadian study in 2012. 28 different landfills were sampled, and PFAS was detected in all 28 samples. the mean concentration of PFOA was around 400 parts per trillion, and a German landfill study where 22 landfills were looked at, and there was a number of different PFAS detected in very wide range of concentrations. So the take home maybe from some of this is that PFAS is in many landfills, if not maybe all of them. Some of the leachate observations, as you could see in the previous slide, it's highly variable. PFAS concentrations between different landfills, but also there can be very big variation within the same landfill. There are some trends observed. The short chain PFAS are typically found at greater concentrations, which is possibly due to the preferential release from the waste. Concentrations in most PFAS is generally similar in old and new waste. However, there are a few PFAS that are found at higher concentrations, likely due to some, in the new waste, likely due to some attenuation or replacement of some of the chemicals that have been used in the past. We see higher PFAS concentrations with increasing pH and total organic carbon. And we see some of the highest PFAS concentrations measured in leachate from wetter climates, which would make sense with some of the leachate or leaching. So again, I think as I mentioned briefly before, the leachate, if we do treat that leachate, and if we're not specifically looking at PFAS, so if we're using maybe a biological process that isn't effective for PFAS, we can actually be converting some of those precursors, which are longer chains that break down into these terminal PFAS constituents, which is what we're a little bit more concerned with. So that's another big consideration here. Real quick on the landfill gas, PFAS has been detected in landfill gas and landfill gas condensate, as well as in the ambient air around landfills and some wastewater treatment plants. Again, this is mostly due to precursors. Some, PFAS such as the fluorotelmer alcohols have a moderate volatility. So you can see down there the PFOA, the vapor pressure is relatively low. We shouldn't see a lot of that. However, it's a couple orders of magnitude higher for 8.2 FTOH, which can break down into PFOA. So some of those precursors have higher vapor pressures and can be seen in the landfill gas. There is significant PFAS emissions that have been calculated from wastewater treatment plants and landfills on the order of greater than 1,000 grams per year. With that, we'll jump into some of the PFAS management and remediation strategies. We'll talk a little bit about some of the different technologies and strategies here, and then toward a little bit later in the presentation, we'll kind of address some specific considerations for leachate, because it does have some specific challenges. So first, we typically want to look at options to reduce or eliminate PFAS at contaminated sites such as AFFF sites or manufacturing sites. We can look at replacement of products or operational upgrades to the structures. We can isolate source areas or waste streams that have high concentrations of PFAS and thereby really minimize or eliminate some of the flow or reduce the volumes that are required for treatment. So some of this, maybe if you're looking at sewers, and sites are different, there's a lot of different ways to minimize those flows and to isolate, but you could look at cleaning sewer lines, which may have PFAS build up in the residues, installing slip liners within pipes, isolating sections of sewers, maybe rerouting sewers around problem areas specific to sewers. And then landfill opportunities, which again, we'll touch on a little bit later, but you can look at evaluating your waste acceptance, additional testing there. You can identify and segregate cells with PFAS concentrations. So again, some of the different cells within the landfills can have very different PFAS concentrations depending on what waste were accepted. The and then obviously leachate minimization activities, looking at daily cover, intermediate cover, accelerated final cover to reduce the total amount of leachate, making sure that your stormwater diversions are not designed and implemented correctly, as well as looking at working phase geometry and different construction techniques that can be used to reduce the overall volumes of leachate, and therefore the volume that that you need to manage potentially for PFAS. So remediation, after looking at kind of some of the source control or reduction or elimination, you know, your next step is potential remediation or looking at remediation options. There are many techniques that are used to remediate hydrocarbons and solvents. These are typically not effective for PFAS because of the strength of that carbon-fluorine bond, as well as the low volatility for a lot of the terminal PFAS. You also have the potential risk to making the site worse by generating more terminal compounds from those precursors and or more mobile species that could migrate off the site if we're looking at groundwater. Bench testing and pilot testing are usually recommended before any full-scale application. So sediment, soil sediment remediation, I'll move maybe a little bit quickly through some of these slides, but this is basically you can have excavation dredging with off-site disposal. It's easy to understand why landfill acceptance of PFAS impacted material could be a sensitive issue, and you know, some of those options are likely drying up. You can look at solidification stabilization, so making sure that we bind that PFAS so that you know, a majority of it or most of it is not leachable and is bound up within that stabilization binder structure. And Golder's, you know, we're working with some companies looking at some of these binders and working on some of the research there. Disposal of the soil or sediment as a hazardous waste is often only a consideration for very small volumes. Incineration is also another feasible option. It does require very high temperatures for the PFAS destruction to break that carbon-fluorine bond, in some cases above 1,000 degrees C. And again, this is generally due to cost, is it's only feasible for small volumes.
Well, on that note, Ryan, would municipal incinerators, I'm not sure if you're familiar with that, but would they be able to achieve these kind of temperatures, or is this just not on? And second part of the question, incineration, I gotta assume something like a cement kiln actually can achieve these temperatures, although they may not want to take it.
I think that they've been looking at possible destruction within cement kilns. Part of it too is there's not one temperature where, you know, you're magically destructing all the PFAS. There's different temperatures for each one of them. Another concern here is when you do destruct those PFAS compounds, a lot of times you're generating an acid which can cause issues with the materials of construction of the incinerator. So you know, there are some incinerators and high temperature incinerators that can deal with this, but you know, you can't just send it to any incinerator. So another soil sediment remediation on-site engineered stockpiles or cells and caps is a very common management philosophy. we're trying to limit the infiltration, precipitation from surface water and groundwater and leave the material in place. Obviously, this will still generally generate a PFAS impacted leachate in many cases that could need to be managed for some time. So we're still generating some of those residuals here if we're putting it in on-site cells. Other soil sediment remediation, again, we talked a little bit about some of the solidification and stabilization. You can use activated carbon to help stabilize, or granular activated carbon or powdered activated carbon, different binders, cements, bentonites. There's also a number of different sorbents and proprietary blends, Rembind, mat care, iron oxide, organoclays, but the long-term leachability and geotechnical considerations here are usually key. Soil washing is another potential option. It's pretty highly dependent on the soil structure, and the efficiency decreases with increasing PFAS chain length and precursors. Pretty obviously, if you're doing soil washing, you're again ending up with a residual liquid stream with PFAS in it that then you would have to manage. Now, maybe, or I guess the in-situ groundwater treatment, there's basically two approaches for in-situ groundwater treatment, permeable reactive barriers or injections. Both of these have pretty limited full-scale application. The permeable reactive barriers, you're using absorption media, which generally will require replacement over time. The injections, which can include advanced oxidation or reduction, you need to be pretty careful about your PFAS characterization and your mass balance. It can be difficult to treat all of these, all the PFAS, and is really only effective for certain PFAS at this time. Another thing that you have to be pretty concerned with, and we've kind of touched on it a couple times with precursors, you run the risk of converting those precursors into a terminal PFAS component. So really, you run the risk of creating one potentially more mobile PFAS constituents, as well as higher levels of the PFAS.
Hey, Ryan, just a comment or question for you here. On advanced oxidation or reduction, what specific treatment chemicals are you talking about here? Is this the idea of potassium permanganates or something? Or,
yeah, and I'll add here that a lot of this is kind of on the bench scale and pilot scale at this point, so it's really being evaluated. But yeah, I mean, they're looking at really a vast number of different oxidants and reduction chemicals being injected. Colloidal carbon is another potential injection that can be used and to provide some plume retardation and kind of keep some of the PFAS where it's at. So with that, I'll talk a little bit about some of the ex-situ. So either for treatment ex-situ, and activated carbon is, or sorption using activated carbon is one of the most utilized technologies for the treatment of PFOA and PFOS, specifically in groundwater and drinking water applications. Generally, you're looking at cleaner waters for the use of activated carbon. It has pretty variable removal rates for different PFAS, and there is generally faster breakthrough for those shorter chain PFAS compounds. There can be significant competing ions that will affect the efficiency of activated carbon, and also biological growth can also reduce the carbon longevity. With the activated carbon, and this is kind of becoming a bit of a theme here, but whether you're using regenerable media, or you're using single pass media, you're generating a media or another stream that requires management. So, you know, you're going to require those high temperatures for regeneration of the carbon. And there's also, as Guy had asked before, there's also issues many times with hydrofluoric acid generation during that PFAS destruction, which can cause issues with your materials of construction there. One of the other probably most demonstrated technologies for drinking water and groundwater is ion exchange. This requires a significantly lower empty bed contact time when compared to activated carbon. So that means we can have vastly smaller carbon beds and carbon columns, reducing capital cost. These also, the actual media itself has significantly higher cost typically than the activated carbon, but on the other side of things, they have generally much higher loading rates, so they can load a significant amount more PFAS onto the same volume of ion exchange material. Similar to the GAC, there are different removal rates for different PFAS, but this is much less pronounced for the ion exchange materials, and again, competing ions and biological growth can limit the media longevity. There's both single and regenerable media available. The regeneration can create a highly concentrated liquid waste with PFAS, and the single-use media then, if you're using single-use media, that's going to require disposal or further management when it's spent. So membrane filtration, reverse osmosis is very effective for removal of PFAS and precursors. You're removing most everything in the water. That can be a very good thing in that you're likely sort of future-proofing sometimes yourself against potential future constituents that might show up. Maybe not all of them, but generally, if something comes up in the future, it's pretty likely that a reverse osmosis system is going to remove that. On the other side of things, that can be a disadvantage, that sometimes you're creating such a clean water that it can have issues with toxicity and passing toxicity test. Nanofiltration is also effective. It generally provides lower removal rates. And you know, two of the big considerations when it comes to reverse osmosis is really the requirement for pre-treatment to protect the membranes. There are some systems that can treat water with generally significantly less pre-treatment, but generally RO is you're gonna require a significant amount of pre-treatment before you send water to the membranes. And then the other one is, okay, that's great. We created a very clean permeate stream, but now we have a concentrated brine that we basically put all of the PFAS in this smaller, lower volume stream. And now what do we do with that? Evaporation is an ex-situ option. Thermal evaporators can utilize biogas from a landfill. They can also utilize waste heat or other low cost energy sources. Obviously, you know, in the picture here, we're showing an evaporator that's the lower picture, you know, discharging to atmosphere. That we could have some issues with the precursors being volatilized within that stream. The upper picture there, that's a mechanical vapor recompression evaporator. So we're taking that steam, we're recondensing it down and creating a relatively clean water stream, although there may be some precursors and PFAS in that could then be, that would then require treatment, but we have stripped out a lot of the complexity of the water. The mechanical vapor recompression evaporators you know, are much less energy intensive because they're recovering all of that heat from the steam to drive to the head of the process, essentially. yeah, I think I mentioned, so the treatment may be required on the vapor or the condensed liquid from these evaporators. And even with that treatment, you also, at some point, you can only reduce it so far, and you have some concentrated PFAS residual management required. So this is precipitation, flocculation, coagulation. These technologies are more experimental at this point. However, I'd say it's considered partially developed. Golder is involved with a number of different technologies. These experimental technologies, from soil treatment and in situ and ex-situ treatment to liquid waste streams. For this particular one, the precipitation, flocculation, different technologies, you're forming a microflocculant that then absorbs some of the PFAS, and then you're removing that by settlement or filtration. These generally have lower removal rates, and you're not able to get down to ultra low levels. And as is becoming the theme here, you then have a sludge with the PFAS in it, a lower volume sludge that you need to manage. One of the technologies here that I think is pretty promising for some complex wastewaters is electrocoagulation, specifically with zinc blades, which is being looked at for PFAS and showing some promising results. Another oxidation and reduction processes can be done ex situ. This is again partially developed, and there's a lot more research needed. The significant benefit here is that you can provide actual destruction of the terminal PFAS, and so you're not just transferring it from one media to another. One of the I think pretty promising technologies here is electro-oxidation with specifically with boron doped diamond blades. So that sounds expensive, and it is, but those coated blades then there's some good results, at least on the bench scale, showing destruction of PFAS with some fairly complex wastewaters. So in talking, so we've touched on, and there are other emerging technologies, plasma and some of these other ones. Again, these are all pretty experimental at this point. But many of the technologies that we discussed, there's some residual that's formed. And so, what do you do with that residual? Well, evaporation is one option. You can concentrate that residual up further. There's a limit to that then. Once you get down to this low volume, if you will, you're pretty much looking at incineration at a proper incineration facility, or solidification stabilization to try to bind that PFAS so that it doesn't release back into a landfill or back into the environment. So now I'll talk a little bit about some of the PFAS challenges specific to leachate. The GAC and the IX that we talked about are pretty proven for groundwater or drinking water. However, they don't work near as well or are really feasible for some of the leachate. So we'll kind of get into that a little bit. There is PFAS removal challenge that complex nature of the leachate and the highly variable water matrices within different landfills and even within the same landfill. Obviously, that's impacted greatly by the waste that the landfill is taking, whether that's municipal solid waste or other. Not only is there great variability with different landfills accepting different waste types, but there's also a lot of variability over time as different waste decomposes. So this graph shows many of the different variables that change during the life of maybe an individual cell. And PFAS can also be pretty variable as can other constituents that would impact treatment, the different treatment technologies. So while maybe in some cases PFAS can be more stable, if some of these other constituents are very variable, it can have a big impact on your treatment technology or strategy. So with that and those challenges involved with leachate, really reduction and elimination of high strength sources should be a very high priority. Evaluating those special waste acceptance, segregating cells, leachate minimization, recirculation, potentially with some solidification or stabilization. Obviously, if we're recirculating the PFAS, you know, we can be cycling up PFAS concentrations, but at the very least, at least we're leaving it within the landfill cell. And then I would say that there are currently very few leachate treatment systems that have been designed specifically around PFAS removal. However, there are a number of different reverse osmosis systems that at some existing landfills that have been shown to achieve very good PFAS removal, as we would expect with a reverse osmosis process when they sampled PFAS. So again, you know, this is showing some very good two-pass membranes, but some very good removals down to non-detect in the second pass for leachate in the permeate. As we mentioned before, one of the big challenges here really is, okay, great, you got a clean water, but we still have the brine with an even higher concentration of PFAS. So kind of touching on there is a wide range of different management and technology options with a range of different that are in a range of different development phases, from experimental through more developed and full-scale applications, and selecting the right application or option can be critical. Some beyond cost, you know, your capital and your O&M cost and your actual removal efficiency, there's a number of different considerations that should be evaluated. Flexibility, whether or not the treatment system or your strategy can address the potential future contaminants of potential concern, or maybe treat to potentially lower discharge limits. We've all seen the regulations and how a lot of them are pretty fluid at this point. So what we're being required to treat to now may not be the same limit in the future. Overall treatment efficiency, safety is obviously a concern, reliability of the system, and its ability to react to system upsets. We've got complexity and maintenance requirements. These are just really a few. I'll touch briefly, specifically on some of the flexibility. Not only do we want to potentially look at the flexibility of different systems to address either lower standards in the future or additional PFAS or other parameters, but also, you know, the flexibility with regard to flow. If the flows change, how easy is it to adapt that system to the flows, and also, you know, can that system be used at other sites where maybe there are issues? So these are a number of things to look at. This is a one way to kind of do some of that evaluation. This is just kind of an overview. This is a goal set plot that can help with the comparison of different options and kind of help get that stakeholder buy-in. Within each one of these categories, obviously, you can drill down into it, and you know, you can have a number of different criteria and weighting factors, things like for the environment, your carbon footprint, secondary waste. I won't, you know, touch on that too much, but a number of different things to look at when you're looking at potential management options. So with that, that brings me to the end here, and I'll pass it back to Guy, or if there's any questions.
Right, okay, hey, thanks a lot, Ryan. So I invite you, listeners, if you have a question or if something's, feel free to type it in. There's no question is a silly question. I ask many silly questions myself, and we get great answers. So please type them in. In the meantime, just before we, I have a few questions myself, but your last slide there, I know that's the gold set tool, but the concept of evaluating options and considering social, economic, as well as environmental and technical issues is, that's now, I don't know, it's a more sustainable approach to looking at how we do things. And I'm a big fan of this approach because we can't just go on treating everything willy-nilly and spending a fortune here if we don't have real clear benefits to ourselves socially and then environmentally and economically, for that matter. So on that note, tomorrow we do have a talk by a fellow, Richard Romer, who's, I think he's living in British Columbia now, but he certainly has a lot of experience from the Netherlands where they've moved more into this kind of approach to environmental assessment remediation. So I invite you all to join us for our free GeoPro talks tomorrow at 10 a.m. Pacific time. In terms of questions, man, oh man, I know we've only got a couple minutes here, Ryan, but your second last slide about the options, if you could just flip back to that, on the, in terms of flexibility, no, you go to the next one, Hid. In terms of flexibility, I think these had to do with treating the liquid waste stream, but you mentioned a few times that reverse osmosis, i.e. membrane filtration, it looks like it's a proven technology. It can address most of the COPCs, contaminants concern. It's the most flexible. Unfortunately, it's the flow rates it can handle are the lowest, and I take that to mean that translates directly into cost. If you want it done right, it's going to cost a bundle. Is that fair to say?
Yeah, your reverse osmosis is going to be an expensive treatment option. I guess maybe to elaborate a little bit on the flow, really, I guess I should have flow variability there. So your membrane process is, if you have a lower flow rate, it kind of is good for treating a consistent flow rate through time. So if maybe you have, just for example, one of your cells open or groundwater remediation, you get a lot of rain, it's a little bit more difficult to ramp up and ramp down with a reverse osmosis system. As well as you mentioned, that can have some high cost associated.
Well, and that's kind of the, my second question is, it's going almost back to the beginning of your talk today about landfills and wastewater treatment plants. I mean, municipal landfills and wastewater treatment plants, this is a big burden on our, municipalities, which have, I dare say, they have limited financial resources to be spending on upgrading landfills and their wastewater treatment plants. So if you mentioned, for example, one of the studies showed that about half of the wastewater treatment plants have PFAS in their leachate, and they're discharging directly to sanitary, meaning they're ending up in potentially in landfills or wherever. Holy crap! We're talking about if everybody goes the way Michigan's going and requires you to treat your wastewater treatment plant effluents, we're talking major resource. Major economic burden, let's say, on so much of our economy here. I'm just flabbergasted. How do you see this going? Do you see this as we're going to go this way and our taxes are going to go through the roof, or what do you think?
Yeah, I think that it's going to be a major challenge to the industry. It's whether or not some of the cost will play into that. I think it will be a large cost. Hopefully, it will be passed on either in taxes or in higher tipping fees for many of the landfills. But yeah, I think this is looking kind of into the crystal ball and seeing where regulations are going. I think this is going to be a big cost potentially to a lot of different landfills. And you know, there are many landfills that are below the current limits for PFAS. So you know, it's not going to hit everyone, but there's going to be that there is a lot that would be impacted.
Well, yeah, I mean, just thinking out loud, I don't think I was the only one that used Scotchgard in the 1970s on my couch. So, I mean, there's no reason that virtually every landfill has going to have PFAS in. I also took one little note here about, you mentioned about trying to prevent contamination. But then you said something about, for example, municipalities could clean their sewer lines, assuming that the sewer lines might have pockets of residuals full of PFAS. If I heard you right, man, I mean, if you clean your sewer line, what do you do with all the goop you generate? That's all got to go somewhere and be treated. So again, the costs start getting up there. Is that right? Or were you talking about just industrial sewer lines or something?
I was referring more to industrial sewer lines, but they're both going to be applicable. A lot of times, and we've seen this at you know, some old manufacturing facilities with very old pipes, and you know, they almost don't look like pipes on the inside anymore. There's a lot of material, and that can be one source for PFAS. So you know, obviously there's a number of different options to look at, and the site-specific constraints and factors play into that to a large extent.
Interesting. Well, I can just we don't have many questions coming in, so I just want to point out to people that have been watching here, or if you're watching the recording later, if you have any questions about anything Ryan said or any of the other PFAS presentations, feel free to send them in to info@geoenviropro.com. That's info, I-N-F-O, at geoenviropro. You can see how to spell it on the screen there, .com. And I'll get them off to Ryan or the other folks that did the presentation here, and we'll get back to you. So just to wrap up, I mean, we're just past the hour here, so I want to thank everyone for joining us for this series. If you have any questions or comments, I think we'll be sending out a little questionnaire later on, but if not, feel free to, again, send them in to info@geoenviropro.com, and we'll take them into consideration. Any topics for future webinars would be nice too. And I want to thank you, Ryan, for the presentation today, and we'll say goodbye to everybody and see you next time.
Thanks, everybody.
All right.
Take care, guy.